for radical equations, we're looking at things of form root x equals 1, something where you have a radical on top of the equation. Remember, radical comes from that same root radix as root does. We're still talking about bases. We're still talking about taking roots of things, as it were, which is why we get that name. And to do this, we have a pretty followable process where what we want to do is arrange the equation to isolate one radical on one side, then raise both sides to the nth power, whatever n is in terms of that radical, to remove that isolated nth root, solve the resulting equation, where sometimes bringing in that power means there are still roots to chase around. You have to do steps 1 and 2 again. Then, to be sure, we can check the solution. So, let's get an example with this type of process in action. So let's solve the square root of the quantity 1 minus 4x minus 2 equals x. Okay, so the first thing we want to do is isolate that radical, which isn't the nicest radical, but we'll make it work, right? So, we're going to end up with 1 minus 4x is equal to x plus 2. So we want to bring that 2 over so that we can get rid of that guy as easily as possible by squaring things. Technically speaking, we could multiply both sides by that, but it would just move it. Sometimes algebra is just moving things, but usually we like to move things with a purpose, or remove things, which we get here by squaring both sides. So, if we square that left side, we'll have 1 minus 4x. And if we square that right side, we'll have x plus 2 squared. Or 1 minus 4x is equal to x squared plus 4x plus 4. So I think I mentioned in a different video, but I can't remember. Anyway, from there, what we're going to want to do is put this now quadratic type thing back into a standard quadratic form, where we should note here that technically speaking, much like when we were talking about rational things being kind of like linear and quadratic equations, but there are important gaps. In this case, this is very close to being a quadratic, except because of where we started, we have to ignore any negative possibilities, and that may come back at the end. Anyway, I'm going to pull over the 4x, pull over the 1, and this will become 0 is equal to x squared plus 8x plus 5. And I can't add. That should be a 3. It happens to everyone. Anyway, with that being as it is, we have a few different approaches. For me, I see a 1 and an 8. Yeah, you could just jump straight to the quadratic formula if you want to, but I see this as an opportunity to try out completing the square again. Feel free to, well, quadratic guys this thing on your own time if you'd rather do that. But anyway, what I'm going to do here is note that since b is equal to 8, I am going to take that value and try to get 1/2 of that squared with the constant, and to do that I need 16. I've got 3, so I'm going to add 13 to both sides. It's not the most obvious thing in the world, but it's what I'm going to do here. So I'm going to add 13 on the left side. 0 becomes 13. X squared remains x squared. 8x remains 8x. And then 3 plus 13 is 16. So this becomes 13 equals x squared, x plus 4 squared. So now we're back like we were in that original completing the square problem, where to finish this off, we're going to take the square root of both sides. So we'll have plus or minus root 13 is equal to x plus 4, or negative 4 plus or minus 13, root 13, is equal to x. And you might think to yourself, okay, that's our solution set is the 2 of these. But let's be careful here. I'm going to leave this to you to check to be sure, but you'll find out that if you plugged in that minus value in there, this guy here wouldn't be very happy about it. This wouldn't work. It fits fine in this part, but remember, we made some important adjustments to what we're allowed to do by getting to that point. So actually, the only value that's valid will end up being negative 4 plus root 13 as a value for x. And from here, a natural extension of this is to wonder, well, if we can handle the 1 over types of powers, the standard radicals, what happens with non-standard rational exponents? And the answer is pretty close to the same thing, but just to be sure, that's what we're looking at next.